I welcome you all in this lecture on block diagram algebra, which is part of modeling and simulation of dynamic system course which you are going through. Previous few classes we have seen how to find out the transfer function for a say first order system, then transfer function for the second order system. The block diagram algebra basically helps us in finding out the transfer function of a complicated system, that is system involving many components. If that is there, then with the help of block diagram algebra we can find out the transfer function for that. So, here in this lecture I will be giving you initially some introduction on the block diagram. Then we will be seeing how can we draw the block diagram of a physical system, and after that we will be looking at the various ways of reducing of the block diagrams. Okay. So, this is how I intend to go here. So, what is a block diagram? A block diagram of a system is actually the pictorial representation of the functions performed by each component and flow of signals. Okay. So, it essentially pictorially represents the flow of signals and the function performed by each component. Block diagram also represents the interrelationship that exists among the various components, and it indicates more realistically the signal flow in a system. So, suppose the input output behavior of a linear system is given by a transfer function, say Gs is equal to Laplace transform of the output divided by the Laplace transform of the input. Here, as I said, input to a linear system has Laplace transform Ys, and the output of linear system has Laplace transform Xs. And of course, when as I have been telling you that when we are finding out the transfer function, we assume that all the initial conditions are 0. So, here suppose we have a block and block is representing a transfer function, say Gs, and say the input to the block is say Ys and the output is Xs. Of course, Ys and Xs are the Laplace transform of the input and output signal. Then here we define the Gs as Xs upon Ys, that is the ratio of output by input signal, Laplace transform of output signal divided by Laplace transform of the input signal. It is a very convenient graphical representation, of course, the one which we are talking about, block diagram, and here as I said the signal into the block, which we call it as the input signal, is Ys, and the signal output of the block is represented by output Xs, and the block itself represents the transfer function. Now, we need to remember certain points about the block diagrams. The flow of information is unidirectional from input to output. That is, the flow of information goes from input to output in the, that is the unidirectional. This is not the bidirectional way as we have seen in case of bond graph, where we have the effort and flow both communicating. If one end has got the effort information, then other end has got the flow information in the case of bond graph. But here, as I said, we have the flow information is unidirectional from input to output. If you remember in case of bond graph, we have seen that if your bond is like this and if your causal structure is like this, then we say that this end is receiving flow, whereas this end is receiving effort. Okay. So, here we have the both way information. Now, a complex system with several non-loading element is represented by the interconnection of block for the individual element. Okay. And the blocks are connected by lines with arrows indicating the unidirectional flow information from output of one block to the input of the other block. So, this is what I mean by it, that is, if say you have a block like this, you have a certain input to this block, then output from this block, then you have another block like this and another block like this. Okay. So, you can have this type of cascading. Now, in a block diagram, summing and differentiating of signal is represented as here. In fact, I am showing you the differentiating of the signal. Okay. That is, if a signal A is coming say from here and a signal B is coming from here, here this is plus and this minus sign basically indicates that this signal will be A minus B. Of course, if we have the symbol here plus, then it will be a summing signal. Okay. So, we have the summing and differentiating signal can be represented here. Likewise, the takeoff point of a signal is represented as here. So, from here we can take the same signal value here. Okay. So, this is how the takeoff point is represented. Then let us see the block diagram of a closed loop system. Okay. Suppose here there is a input to the system which is represented by Ys. Okay. And say there is an output of this system represented by Xs. The transfer function here is say Gs. Okay. Then what we do is actually is that through this branching point I take the same signal Xs from here, and through a summing point here I subtract this output signal from the input signal. So, here what I get error signal Es, which is nothing but Ys minus Xs. So, the Es there is basically Ys minus Xs. Okay. And okay. So, the and here you can see that the output of this block diagram, that is Xs, is being fed here. Okay. To the summer to find out the error. So, this type of block diagram is what is called as the closed loop system. Okay. You may ask some practical example, or why we are going for say this closed loop system, or what is the practical example of this closed loop system. So, let us look at this figure. Now, you see that here the output is Xs, and then this output basically Xs is multiplied by this Hs, okay, certain gain, okay. It is multiplied with certain gain, and whatever we get, say let us it is Bs, and then this Bs is taken to the Ys, subtracted from Ys. Now, this type of system, if I say take the example of say temperature control of a room, fine. Then suppose the signal here Xs which I am getting, okay, I am getting say the temperature, this Xs signal in the form of a say temperature, okay. Now the thing is that suppose I want to feed it here with input setting, usually we do with the same with the help of some pots, okay. So some input signal is say some voltage, then this temperature signal can be converted into a voltage signal. So basically this Hs does the role of conversion of this temperature signal into a voltage signal, and then of course this can be compared, error can be found out, okay. So this type of signal is what is called as the closed loop system. Closed loop system means that where the closed loop systems are usually the error driven system, or you can say that where the output has got the influence of influence on what is going inside the block. That is what is we mean by the closed loop system. So let us define some transfer functions, and say in this case the open loop transfer function is defined as the ratio between the Bs and Es here. So you can see that the Bs is input to the summer here, and Es is the error signal, that is Ys minus Bs, okay. So this is what is called as the open loop transfer function, and here you can see that the Bs by Es is given by multiplication of Gs and Hs. So this is basically Gs Hs, or you can see that this Bs is basically Hs into Gs into Es, alright. So that we can find out. So this is what we call it as the open loop transfer function, okay. I can also define the feed forward transfer function, and this feed forward transfer function is Xs ratio of Xs by Es, okay, that is output by this error signal, and this Xs by Es is what is called Gs, okay. And if the feedback transfer function is unity, then open loop transfer function and feed forward transfer functions are same. So you can see that if I put this as unity, then whatever we get here, this and this both are going to be the same value, okay. Next is the closed loop transfer function. Now this closed loop transfer function is basically defined as the ratio of Xs by Ys, okay. So to get the derivation for the closed loop transfer function, okay, we can find out the input to the forward path. So this is the forward path. So what is the input to the forward path? This input you can find out, this is Ys minus Bs, okay. And what is this Bs? This Bs is nothing but Hs into Xs, okay. So the input to the forward path is Ys minus Hs into Xs, okay. And what is the output of the forward path? Output of the forward path is Xs, okay. So I can define Gs as Xs upon Ys minus Hs Xs, okay. So here I can define as you can see the Gs is equal to Xs, which is output, divided by the input here, and that input is Ys minus Hs Xs. Okay. So, from here I can get Xs as Gs Ys minus Gs Hs Xs. Okay. So, I can take Xs Xs one side. So, here what I get is 1 plus Gs Hs is equal to Gs Ys. Okay. So, what is my ratio of Xs by Ys, that is the output by input. So, this is my Gs upon 1 plus Gs Hs. So, this is what we get here. So, Xs upon Ys is Gs upon 1 plus Gs Hs. So, this way we can find out the closed loop transfer function. So, here you can see the output of this system is Xs and the input to the system is Ys. Okay. So, from here I can find out Xs as Gs upon 1 plus Gs Hs into Ys. And what does this means? This means that the output of closed loop system depends on both the closed loop transfer function and the nature of the input. We can take an example to understand this further. Say if the forward path transfer function of a system is given by this one and there is a negative feedback is 5s. Okay. Then find the transfer function of the complete system. Okay. So, here basically the overall transfer function will be Gs upon 1 plus Gs Hs. So, Gs is given as 2 by s plus 1 and 1 plus Gs again 2 by s plus 1 and Hs is given as 5s. So, we can simplify this and this way we get the overall transfer function for the system. Now, the question is what should be the procedure to draw the block diagram? How can we draw the block diagram for any physical system? Okay. So, to do that here are some guidelines. What we can do is that we can write the equation that describes the dynamic behavior of each component. Okay. So, this we can do. Then we take the Laplace transforms of these equations assuming initial conditions to be 0 and we represent each Laplace transform equation individually in the block form and finally we can assemble the elements to complete the block diagram. Okay. So, first we write the equation which describes the dynamic behavior of each component, then we take the Laplace transform assuming initial condition 0, then we represent that Laplace transform as a individual block form and of course, then we can assemble all the blocks okay, in order to complete the block diagram for the whole system. Let us take an example. Suppose this is a RC circuit okay, and to this RC circuit there is a say applied voltage Vi and say I am interested in finding out observing the voltage across the capacitor say Vo. So, first step that we write the dynamic equation for the system. So, here you can see that I can write expression for the current I is equal to Vi minus Vo, here is Vi voltage, here it is Vo. So, Vi minus Vo divided by R okay, and the Vo I can write integral of I dt by C, not same as that is the charge across the capacitor plates divided by the capacitance. Now, in the next step what we do is that we take the Laplace transform of both these equations. Okay. So, the first equation, if I take the Laplace transform, so this is 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 equal to Vis minus Vos divided by R, and for the second equation, if I take the Laplace transform, it is Vos is equal to I by S, Laplace transform for this is I by S into this C. Okay. Now, let us come to the third step, that we represent each equation in the form of block diagram. So, the first expression you can see Is is Vi minus Vo by R. So, you can see that here we are taking the subtracting the two voltages. So, subtraction I can do across a summing element. Okay. So, my Vi is positive here and Vo is negative here. So, I use a summer here which differentiates this voltage Vi with Vo. Okay. So, here and then this Vi minus Vo is divided by R. So, I use a block diagram here, a block whose this transfer function is say 1 by R, and what I get is Is. So, this is my Is. Okay. So, this part of the block diagram represents the first equation. Okay. The second part of the block diagram I can represent here, Vo is Is by Sc. So, here Vo is my output and say Is is my input, and 1 by Sc is the transfer function. Okay. So, this block diagram represents this equation, whereas this block diagram represents this equation. Now, I combine these two blocks. Okay. So, how can I combine? I can combine here that see the output from this block is Is, and this output is same as the input for this block. Okay. So, I combine here. So, this Is is same as this one, and here the output of this block is Vos, and remember here I am subtracting Vos. So, I just take a signal from here and subtract it through Vos. Okay. So, this way I can combine both of these block diagrams in order to make a single block diagram, and of course, this single block diagram represents the block diagram for the whole system. Okay. Now, there could be various ways, or there could be various ways in which we can simplify the block diagram in order to find out the overall transfer function. Okay. So, here are certain equivalented original block diagram, and certain equivalent block diagrams are given. So, here you see that say there is a first block with transfer function G1s, and say input to this is x1 and output to this is x2. Similarly, there is another block whose output is x3 and the input to this is x2. Okay. So, this whole thing can be represented like this. Why we can represent it like this? Because we can simplify these equations. Say for the first block I can write x2 is equal to x1 into G1s, and for the second block I can write x3 is equal to G2s into x2. Okay. And then I can substitute for x2 here. So, this is G2s into G1x into x1. So, this is x3. Okay. So, what does this means? That both the blocks can be combined, and the combined transfer function is G2s into G1s, and output is x3 and input here is x1. Okay. So, this is how it is represented here in the first figure. Okay. So, we can write it this way or we can write it other way also. Now, let us look at the second figure. Now, here say there is input x1, here we are there is a summer, okay, with sign plus or minus, x2 is there, g is here, transfer function, and here say x3 is here. Now, what I am doing here is basically I am taking this summer ahead of this block, okay. So, if I write if I do this, then what I have to do is that here I have to create one additional block with the transfer function g, okay, and we can see the equivalences of both the blocks, okay, that is the original block and the reduced block. So, if you look at the first one, for the first case x3 is equal to, it is g times what we have the error one, okay, there input to the g, that is x1, then what we have is plus minus x2, okay. And if you look at the second one here, then in the case of second, what we get x3 is equal to, this is g times x1. So, g times x1, and here we will have plus minus what, g times x2, g times x2. So, from here basically I can take g out. So, this is x1 plus minus x2. So, we get the same expression, okay. So, this is why this is equivalent for this block. Similarly, here you see that in this block there is a point here, we are taking this x2 signal, tapping this x2 signal from here, okay. Now, if I take this tapping point from here to say here, I have to introduce one additional block here with the transfer function as g, okay. So, this is how we explain, and again the output in both the cases, that is the original block and the equivalent block is same. So, in first case you can see that this x2 is basically g times x1 and we are getting the signal x2 here. So, in this one you can see that this x2 will be g times x1 same as this one, and we are typing here x2, but here if we are typing it from this point it is x1, okay, and so this x2 is basically has to be g times of x1, okay. This x2 is g times of x1. So, if I am writing in terms of x2, I have to put here g times of x1. So, this is how this is done, okay. Similarly, in the here suppose you have a point, tapping point here, say at before this block, and if you want to take it after this block, okay, then again you have to introduce one block with transfer function 1 by g here, okay. So, if you are taking it if you are taking this point back, then the transfer function has to be g, and if you are taking it ahead, then the transfer function has to be 1 by g. So, here again we can see x2 value is going to be g x1, and of course, here x1 is already there. So, here this x2 is g times of x1, and here this x1 will be 1 by g, okay, 1 by g times x2, and x2 is again g x1. So, here we will be getting x1 only, okay. So, this is how it is. Next, suppose we have the original block like this, okay, that is we have a summer here, okay, and say summer, if we want to take behind of this block, okay, g, then this is what we have to do in this feedback signal. Here we have to divide this by 1 by g, okay, and again we can establish the equivalence of both of these, okay. So, in first case it will be x3 will be what, it will be g x 1, okay, plus minus x 2, okay. And in the case this second figure, what we will have is x 3 is equal to g times what we have x 1 plus minus, okay, we will have 1 by g x 2, okay, or this is g x 1 plus minus x 2. So, this is same as this one, that is why both these blocks are equivalent blocks, okay. And this one we have already seen that in case of a closed loop system, okay. So, in case of closed loop system, the overall transfer function between the output and input is given by here x 2 is equal to here x 2 by x 1 is basically g h upon 1 plus g h, okay. So, g upon 1 plus g h, and of course, this is valid if you have a minus sign here. So, if you have a plus sign, then here the first sign will be negative, and the for the second case, that is the for the positive case, you will be having the negative sign, and for the negative sign negative case you will be having the positive sign. So, this is how this can be represented equivalently by this block, okay. And we can follow all these procedures to find out the transfer function for a system something like this. So, for this system, say y(s) is the output and say r(s) is the input, and in between we have many forward transfer functions, say g1, g2, g3, g4, and there are feedback transfer functions say h1, h2 and h3. So, we can simplify this model as per the procedure which I have just discussed, and we can get the overall transfer function for this system. So, I am not going to solve this, I am leaving this as an exercise to you. So, please try to solve this, okay. And this is the practical application of whatever we have talked in this lecture, okay. If you want to further read, please go through any of the book, either Ogata or Bolton, okay. Thank you.